In the mysterious world of the very small, where reality defies our everyday intuition, the science of quantum mechanics unveils the secrets of the universe. This statement, while simple, hints at the profound implications of this revolutionary field of study. Quantum mechanics, often dubbed quantum physics, delves into the fundamental building blocks of the universe, exploring the behavior of matter and energy at the atomic and subatomic levels. It is a world where the familiar laws of classical physics break down, replaced by a new set of rules that govern a realm stranger than fiction. Our journey into the quantum world begins with a sense of wonder and a willingness to embrace the unknown. The quantum realm is not merely a realm of abstract equations and complex theories, it is the very foundation upon which our reality is built. From the smallest particles to the largest structures in the cosmos, quantum mechanics holds the key to understanding the universe's deepest secrets. In this exploration, we will embark on a captivating adventure, delving into the heart of quantum mechanics. We will unravel its enigmatic principles, trace its historical development, and explore its profound implications for our understanding of the cosmos and our place within it. Prepare to be amazed, challenged, and ultimately transformed as we venture into the extraordinary world of quantum mechanics. Don't forget to subscribe and turn on push notifications to stay updated with our latest explorations. Let's aim for 100 likes on this video to unlock more fascinating content about the quantum world. The birth of quantum mechanics marked a turning point in science. It challenged the established order of classical physics. Scientists encountered phenomena that classical physics could not explain. A revolution was brewing, shattering classical physics and ushering in a new era. Visionary physicists like Planck, Einstein, Bohr, and Heisenberg led this revolution. They introduced radical concepts like energy quantization and wave-particle duality. This revolution continues today, impacting fields from cosmology to computer science. Quantum mechanics presents us with a picture of reality that is fundamentally different from our everyday experience. It challenges our intuitive understanding of concepts like position, momentum, and even the nature of reality itself. In the quantum world, particles can exist in multiple states simultaneously, blurring the lines between what we perceive as distinct entities. One of the most perplexing aspects of quantum mechanics is the idea of wave-particle duality. This principle, demonstrated by experiments like the double-slit experiment, suggests that particles like electrons and photons can behave both as waves and as particles depending on how they are observed. This duality challenges our classical intuition, which neatly categorizes objects as either waves or particles. The concept of superposition further complicates our understanding of reality. According to this principle, a quantum system can exist in a combination of multiple states at once, known as a superposition. This means that a particle, for example, can be in multiple positions simultaneously until it is measured. The act of measurement collapses this superposition, forcing the particle to adopt a definite state. This probabilistic nature of quantum mechanics, where outcomes are described by probabilities rather than certainties, is another departure from classical physics. In the quantum realm, we can only predict the likelihood of certain outcomes, not the outcomes themselves. This inherent uncertainty is not a limitation of our measurement techniques, but a fundamental aspect of the quantum world. Our exploration of quantum mechanics is a journey into a realm of wonder, mystery, and profound implications. It is a journey that will challenge our preconceived notions, expand our understanding of the universe, and open our minds to new possibilities. Along this journey, we will encounter concepts that seem paradoxical, even impossible, from our classical perspective. We will delve into the heart of atoms, exploring the behavior of electrons and other subatomic particles. We will unravel the mysteries of quantum entanglement, where particles become linked in such a way that they share the same fate, no matter how far apart they are. And we will explore the frontiers of quantum technology, where the bizarre laws of the quantum world are harnessed to develop revolutionary new devices and applications. The journey into the quantum is not for the faint of heart. It requires a willingness to embrace the unknown to question our assumptions, and to accept that the universe operates in ways that we are only beginning to comprehend. Yet, it is a journey filled with wonder, excitement, and the promise of profound discovery. Join us as we embark on this extraordinary adventure, exploring the captivating world of quantum mechanics and unlocking the secrets of the universe. The journey into quantum mechanics began in the late 19th and early 20th centuries, marked by scientific curiosity and radical new theories. Classical physics faced anomalies at microscopic scales. Avant-garde thinkers rethought the nature of energy and matter. Phenomena like blackbody radiation and the photoelectric effect hinted at new rules at the subatomic level. The scientific community grappled with these issues, leading to a paradigm shift. Key figures emerged, laying the groundwork for quantum theory. Max Planck, a German physicist, challenged classical physics norms. In 1900, Planck studied blackbody radiation and electromagnetic radiation.
Classical theories predicted infinite energy emission, known as the ultraviolet catastrophe.
Planck proposed a radical solution. Energy comes in discrete packets, or quanta. Energy is emitted or absorbed in fixed amounts proportional to radiation frequency.
This quantization matched theory with experiment and opened new physics perspectives.
Initially a mathematical trick, it became a fundamental aspect of nature. Planck's work resolved the ultraviolet catastrophe and suggested new physics laws. His contributions marked the inception of quantum theory, describing atomic workings. In 1905, Einstein explained the photoelectric effect, building on Planck's ideas. This phenomenon involves the emission of electrons when light shines on a material.
I proposed that light could also be particles, called photons, each carrying energy.
Einstein suggested photon energy is proportional to light frequency. His work earned him the Nobel Prize in Physics in 1921.
In 1913, I introduced a model of the atom that incorporated quantum theory to explain its electronic structure. Up until then, the atomic model had several unresolved issues, particularly in explaining why atoms emitted light in specific quantized wavelengths.
Bohr proposed that electrons orbit the nucleus in certain allowed stable orbits without radiating energy, unlike what classical electromagnetism would predict.
I suggested that electrons could jump from one energy level to another, and the energy difference between these levels appeared as quantized light, or photons. This model was particularly successful in explaining the spectral lines of hydrogen, the simplest atom, providing a quantized explanation for the Balmer series that had been observed experimentally.
Bohr's model was a significant advancement in the development of quantum mechanics. It combined Planck's quantization of energy and Einstein's particle theory of light into a coherent model of atomic structure. This model not only advanced the understanding of atomic physics, but also provided a framework that would be essential for the later development of more sophisticated quantum theories.
My work illustrated the practical application of quantum mechanics at the atomic level, significantly influencing the scientific community's acceptance of quantum theory. My contributions were fundamental in moving quantum mechanics from a theoretical framework to a robust model capable of making precise predictions about atomic behavior.
In 1927, I introduced the uncertainty principle, profoundly changing our understanding of the micro-world. This principle states that it is impossible to simultaneously know both the position and momentum of a particle with absolute precision. The more precisely one is known, the less precisely the other can be determined.
This principle was a direct challenge to the classical idea of determinism, where it was believed that all properties of a physical system could be known exactly. Heisenberg's uncertainty principle introduced a fundamental limit to what could be known about the properties of subatomic particles, emphasizing the probabilistic nature of quantum mechanics.
The uncertainty principle had profound implications, not just for physics, but for the philosophy of science as well. It suggested that at a fundamental level, nature is governed by probabilities rather than certainties, a notion that has profound implications for how we understand the universe.
Heisenberg's work was part of the broader development of matrix mechanics, one of the first complete formulations of quantum mechanics. His ideas, along with those of other physicists like Erwin Schrödinger, who developed wave mechanics, formed the bedrock of modern quantum theory. providing tools that are still used in contemporary physics to describe the behavior of particles at the smallest scales.
My contributions, particularly the uncertainty principle, remain one of the key components of quantum mechanics, illustrating the strange and counterintuitive nature of the quantum world.
As we delve into the quantum realm, we encounter principles that challenge our everyday intuition. These principles form the bedrock of quantum mechanics, providing the framework for understanding matter and energy. Shedding our classical biases is key to grasping quantum mechanics. In the quantum realm, classical physics rules break down. Observation influences the outcome of events. Quantum mechanics has been rigorously tested and confirmed. It underpins many technological marvels we rely on today. At the heart of quantum mechanics lies a profound paradox: wave-particle duality. This principle asserts that particles can exhibit both wave-like and particle-like properties depending on the experimental setup. Waves are disturbances that propagate through a medium, carrying energy and momentum but not matter. Particles are discrete packets of matter, localized in space and time, possessing properties like mass and charge. Experiments like the double-slit experiment demonstrate that particles like electrons and photons can exhibit wave-like interference patterns, even though we typically think of them as tiny localized objects. Perhaps no experiment better illustrates wave-particle duality than the iconic double-slit experiment. In this experiment, a beam of particles is fired at a barrier with two narrow slits, and a detector screen records where the particles strike. Instead of two distinct bands, an interference pattern emerges on the detector screen, characterized by alternating bright and dark fringes. This pattern is a hallmark of wave behavior arising from the constructive and destructive interference of waves. Even more astonishingly, this interference pattern persists even when the particles are fired one at a time, implying that each individual particle somehow interferes with itself. The double-slit experiment led physicists to develop the concept of superposition, a fundamental principle of quantum mechanics. Superposition asserts that a quantum system can exist in multiple states simultaneously until it is measured. This means that a quantum particle can be in a superposition of multiple positions, energies, or spins at the same time. The particle exists in a combination of all possible states simultaneously, defying our classical understanding of an object existing in a single definite state. The act of measurement collapses this superposition into a single definite state, suggesting that the observer and the observed are inextricably linked in the quantum world. The concept of wave function collapse lies at the heart of one of the most intriguing aspects of quantum mechanics: the role of measurement. In the quantum realm, measurement actively shapes and defines the outcome of an experiment. The wave function describes the quantum state of a system, containing all the information about the system's possible states and their corresponding probabilities. Before measurement, the wave function exists in a superposition of all possible outcomes. The act of measurement disrupts this superposition, causing the wave function to collapse into a single definite state. The uncertainty principle, formulated by Werner Heisenberg in 1927, states that there are fundamental limits to the precision with which we can know certain pairs of physical properties of a particle simultaneously. One of the most well-known examples involves the position and momentum of a particle. The more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. This is not a limitation of our measuring instruments, but rather a fundamental property of nature itself. The uncertainty principle challenges the deterministic worldview of classical physics, suggesting that there are inherent limits to what we can know about the universe. Unlike classical physics, where events unfold with deterministic certainty, quantum mechanics introduces an inherent element of probability into our description of the universe. In the quantum realm, we can only predict the likelihood of a particular outcome, not the outcome itself. This probabilistic nature arises from the wave-particle duality of matter and the superposition principle. The probabilities of different outcomes are determined by the wave function, which evolves deterministically according to the Schrödinger equation. This probabilistic nature of quantum mechanics suggests that the universe is not a clockwork mechanism governed by deterministic laws, but rather a realm of chance and uncertainty. Despite its success, quantum mechanics remains a source of profound mystery and ongoing debate. Many fundamental questions about the interpretation and implications of quantum theory remain unanswered. One of the most enduring mysteries is the nature of wave function collapse. While we can describe the collapse mathematically, the precise mechanism that triggers it remains elusive. Another open question is the nature of quantum entanglement, where particles become linked and share the same fate even when separated by vast distances. As we venture deeper into quantum mechanics, we encounter a profound shift in the language used to describe the universe. While classical physics uses algebra and calculus, quantum mechanics employs wave functions, operators, and Hilbert spaces. This abstract mathematical framework is essential for capturing the counterintuitive behavior of the quantum world. It provides a powerful tool set for describing the quantum world with rigor and clarity. We will demystify some key concepts, providing an intuitive understanding of how these mathematical tools enable us to describe and predict the behavior of quantum systems. At the heart of quantum mechanics lies the Schrödinger equation, a mathematical masterpiece formulated by Erwin Schrödinger in 1925. This equation governs the evolution and behavior of quantum systems over time. Unlike Newton's second law, which deals with deterministic trajectories, the Schrödinger equation describes the evolution of the wave function. The wave function encapsulates all the information about a quantum system. Solving the Schrödinger equation allows us to determine how the wave function evolves over time, providing probabilities of finding the particle in different states. Central to quantum mechanics is the concept of the wave function, which provides a complete description of the quantum state of a system. Unlike classical physics, the wave function encapsulates all the information we can possibly know about a quantum system. The wave function is a complex-valued function, and its magnitude squared gives the probability density of finding the particle at a particular point in space at a given time. It evolves over time according to the Schrödinger equation. The wave function provides probabilities of different outcomes when we make a measurement on a quantum system. In quantum mechanics, physical quantities that we can measure are represented by mathematical objects called operators. Operators act on the wave function, transforming it to extract information about the corresponding physical quantity. Each observable has an associated operator, such as the position operator or the momentum operator. When an operator acts on a wave function, it can either leave it unchanged or transform it into a different wave function. The eigenvalues of an operator represent the possible outcomes of a measurement, and the wave function collapses to an eigenstate of the corresponding operator during measurement. Section 5. From matrices to Hilbert spaces, expanding the mathematical landscape. As we delve deeper into the mathematical formalism of quantum mechanics, we encounter the concept of Hilbert spaces, abstract vector spaces that provide a powerful framework for representing quantum states and operators. Hilbert spaces generalize the familiar notion of Euclidean space extending it to infinite dimensions and incorporating the complex numbers. In quantum mechanics, the wave function, which describes the state of a quantum system, is represented by a vector in a Hilbert space. These vectors can be added together and multiplied by complex numbers, just like vectors in ordinary Euclidean space. Operators, which represent physical quantities, are represented by linear transformations in Hilbert spaces. These linear transformations act on the vectors representing quantum states, transforming them in a way that extracts information about the corresponding physical quantity. The inner product, a generalization of the dot product in Euclidean space, plays a crucial role in Hilbert spaces. The inner product between two wave function vectors gives the probability amplitude for the system to transition from one state to another. The mathematical framework of Hilbert spaces provides a powerful and elegant language for describing the quantum world. It allows us to represent quantum states and operators in a mathematically rigorous way and provides the tools for calculating probabilities, eigenvalues, and other quantities of interest in quantum mechanics. Prepare to enter a realm where reality takes an even stranger turn, where the very fabric of space and time seems to unravel. Here, in the heart of quantum mechanics, lies the enigmatic phenomenon of entanglement, a concept so bizarre and counterintuitive that it once led even Albert Einstein, one of the founding fathers of quantum theory, to question its validity. Entanglement, often dubbed spooky action at a distance, describes a peculiar connection between two or more quantum particles, a link that persists even when these particles are separated by vast distances. Once entangled, these particles cease to exist as independent entities, their fates intertwined in a way that defies our classical understanding of space and time. Imagine two coins flipping in perfect unison, their outcomes always correlated, even if one coin were on Earth and the other on the Moon. This seemingly impossible scenario captures the essence of entanglement, where the measurement of one entangled particle instantaneously influences the state of the other, regardless of the distance separating them. This instantaneous connection, this spooky action at a distance, puzzled Einstein and many of his contemporaries. How could information seemingly travel faster than light, violating one of the fundamental principles of special relativity? Was there something missing from quantum mechanics, some hidden variable that could explain this strange correlation without resorting to such bizarre implications? The EPR paradox, proposed by Einstein, Podolsky, and Rosen, challenges the completeness of quantum mechanics. They argued that quantum mechanics must be incomplete, missing some hidden reality. The paradox hinges on locality, the idea that objects are only influenced by their immediate surroundings. Entanglement implies spooky action at a distance, violating locality. Measuring one particle's spin instantly determines the other's, even light years apart. They suggested hidden variables might resolve this paradox. For several decades, the EPR paradox remained a philosophical conundrum, a debate about the interpretation of quantum mechanics rather than a testable scientific theory. However, in 1964, physicist John Bell devised a groundbreaking theorem that transformed the EPR paradox into an experimentally verifiable prediction, setting the stage for one of the most profound tests of quantum mechanics ever conducted.
Bell's theorem, a masterpiece of mathematical ingenuity, showed that if quantum mechanics were correct, and entanglement did indeed involve non-local correlations, then certain statistical inequalities, now known as Bell inequalities, would be violated. Conversely, if the universe were governed by local hidden variables, as Einstein and his colleagues had proposed, then Bell inequalities would hold.
Bell's theorem provided a way to experimentally distinguish between the predictions of quantum mechanics and those of local hidden variable theories, turning a philosophical debate into a testable scientific hypothesis. The stage was set for a showdown between two fundamentally different views of reality. In the 1980s, a series of groundbreaking experiments, most notably those conducted by physicist Alain Aspect and his team, put Bell's theorem to the test. Using entangled photons, they demonstrated with remarkable precision that Bell inequalities were indeed violated, confirming the predictions of quantum mechanics and providing compelling evidence for the existence of non-local correlations in the universe. Section 4. Quantum entanglement in action from cryptography to computing. The profound implications of quantum entanglement extend far beyond the realm of theoretical physics, promising to revolutionize fields as diverse as cryptography, computing, and even our understanding of the nature of reality itself. One of the most promising applications of entanglement lies in the field of quantum cryptography, where it offers the potential for unbreakable encryption. By exploiting the non-local correlations between entangled particles, scientists have developed techniques for generating secret keys that are impossible to eavesdrop on without detection. Imagine two parties, Alice and Bob, wishing to communicate securely. By sharing entangled particles, they can generate a random sequence of bits known only to them that can be used as a key to encrypt and decrypt their messages. If an eavesdropper attempts to intercept the entangled particles, their presence would be immediately detected, as any measurement on an entangled particle would disturb its delicate quantum state. Entanglement also holds immense promise for the development of quantum computers, devices that exploit the principles of quantum mechanics to perform calculations that are intractable for even the most powerful classical computers. Unlike classical bits, which can represent either a 0 or a 1, quantum bits, or qubits, can exist in a superposition of both states simultaneously, exponentially increasing their computational power. Section 5. The Future of Entanglement, Exploring the Frontiers of Non-Locality. As we continue to probe the mysteries of quantum entanglement, we stand on the threshold of a new era of scientific discovery, one that promises to reshape our understanding of the universe and unlock technological possibilities that were once relegated to the realm of science fiction. One of the most exciting frontiers in entanglement research involves exploring its potential for quantum communication, enabling the instantaneous transmission of information across vast distances. While this prospect might seem like something out of Star Trek, recent experiments have demonstrated the feasibility of teleporting quantum states between entangled particles, raising hopes for a future where information can travel faster than light. Entanglement also has profound implications for our understanding of the nature of space and time, suggesting that these fundamental concepts might be more interconnected and less absolute than we once believed. Some theories propose that entanglement could play a role in the emergence of space-time itself, weaving the fabric of the universe from the intricate dance of entangled particles. As we venture deeper into the enigmatic realm of quantum entanglement, one thing is certain: the journey will be filled with wonder, discovery, and the realization that the universe is far stranger and more wondrous than we could have ever imagined. Weaving the fabric of reality, quantum field theory, and the Standard Model. Exploring the quantum realm reveals a profound shift in our understanding of the universe. Quantum field theory and the Standard Model offer a grand vista of particle physics. QFT represents a monumental leap from quantum mechanics. Particles are excitations of fields permeating space and time. QFT explains the fundamental forces of nature. The Standard Model encapsulates our understanding of matter's building blocks. It describes the electromagnetic, weak and strong nuclear forces. The Standard Model weaves together quarks, leptons and force carriers. It predicts subatomic particles' properties and the universe's evolution. Beyond the horizon, unanswered questions and future frontiers. The Standard Model is not the final word in our understanding of the universe. It raises more questions than it answers, beckoning us to explore uncharted territories. One glaring omission is gravity, governing the large-scale structure of the universe. Dark matter and dark energy remain shrouded in mystery, hinting at physics beyond the Standard Model. The quantum legacy transforming our view of the universe. The journey into the quantum realm has been profound, challenging our classical intuitions. Quantum mechanics has shattered the deterministic worldview, replacing it with a probabilistic reality. It has revolutionized our technological capabilities, from lasers to modern electronics. Quantum computing and communication promise a new era of innovation. The most important lesson is the vastness of our ignorance and the boundless capacity of the human mind. Embracing the quantum world, a call to curiosity and wonder. As we conclude our exploration of quantum mechanics, let us carry with us a renewed sense of wonder and a deep appreciation for the profound beauty and mystery of the universe we inhabit. The quantum realm, once a distant and esoteric realm, has become an integral part of our understanding of the world, shaping our technologies, challenging our philosophies, and expanding our horizons. The journey into the quantum has been a testament to the power of human curiosity, the relentless drive to explore the unknown, to question our assumptions, and to push the boundaries of knowledge. It is a journey that continues today, driven by countless scientists, researchers, and dreamers who dare to ask the big questions and seek answers in the intricate dance of the quantum world. So, let us embrace the quantum world not with fear or confusion, but with a sense of awe and excitement for the mysteries it holds, for the discoveries yet to be made, and for the technologies that will shape the future. Let us cultivate a spirit of curiosity, a thirst for knowledge, and a deep appreciation for the intricate beauty and wonder of the universe we are privileged to call home.